Thank you very much for coming and listening to what I'm about to say. I just want to give you a very quick introduction in like a few sentences about what Sonic Pi is. But of course, who here has heard of it already? Wicked, that's wicked, right, cool. There's a bunch of talks already I've given which describe why I've created it. And specifically, like this title here, the live coding synth for everybody. I mean, that really is the goal. I'm trying to be as inclusive as possible to try and get as many people from whatever background or whatever age to be able to have a creative experience with code. That's the ultimate aim. And as such, it was born in the classroom, created for school children to use, to learn programming, to be engaged with programming. But it's been used by all sorts of wonderful communities to do exactly that. So it's not just limited to school children. And actually, that's one of the most interesting things for me is that often parents would come and say, I need to get my son or daughter to look at Sonic Pi. And I'm saying, what about yourself? Right? It's not just for school children. But again, if you want to look more about why I've created it and what it's about, then there are other talks. This talk is about the technical internals of Sonic Pi and what the sort of the ideas I've created and how I've created them and why. Because it's be the first time I'm talking to a fully technical audience. Normally I talk to school children or to parents or to teachers. And there I have to be very sort of constrained by the language I use and the abstractions I describe, because obviously they don't have the same kind of level of technical ability as the majority of you do. So hopefully you can enjoy a little bit about the internals of Sonic Pi and why I've created it. So let's continue. These are the few things I'm going to talk about here. Let's get some feedback from that. I'm going to talk about these 1, 2, 3, 4, 5 things: play, sleep, in thread, with effects, live loop, and Q-sync. Right. By the end of this talk, you'll understand all of these things. So let's look at play and sleep. So the most simple thing you do in the classroom is this. Now, this is really important because I don't know if you've ever been to the classrooms recently, but it's depending on the school. Like I've been to a load of different schools recently. There's lots of different behaviours of children and different controls of teachers and different attitudes and different social structures, and depending on the age. But one thing that's quite common is that the teacher doesn't have much time to impart some information to the class. Right? They're like clapping and trying to get the children quiet. And then when the children are quiet, what are your 1 or 2 sentences to get children started programming? Right? If they are open up Eclipse, or open up Emacs, open up Vim, right? IntelliJ, whatever, right? You're screwed. So because like when you open one of these things, it's like which project, what kind of project, which style of project, where am I putting the project, all this sort of stuff, which is, I guess, kind of useful to some professional programmers. I really hate that stuff personally, but you guys, I'm sure some of you appreciate the complexity of your editors. So the goal with Sonic Pi is to make something trivial, right? So you open it up, and it just opens up like this. This is the full screen mode, right? It's just a normal app, look, with some buttons which normally look like this. Seem to be getting feedback when I stand over here, so I'll try and avoid that. Yeah, there's just a normal app here, and so you can enter into full screen mode for performance purposes and get rid of the buttons. But you really just need to write play 80, right? Just 2 words. Play means to have fun, and 80 is how much fun you want. You press run, and you get a ping, right? And that's it. That's the first creative experience with code. And kids, they go nuts. Like, that's amazing. Because sound is something they can understand and appreciate. But not just kids, but everyone appreciates making some sounds. And the thing is, right, I don't know, have anyone heard of Overtone, the system I built before with Jeff Rose? That was wicked. And I did a bunch of talks and workshops with that. And it was great because he'd walk around the hotel lobbies or in the rooms, in the corridors, and he'd hear these noises coming from people's rooms, like, and it's like, yeah, people are having fun with Overtone. But that's all they could do, right? They could make these hideous sounds. And so the other goal of Sonic Pi is to actually be able to make more interesting sounds with more ease. And the simplest sound is just a sine wave. It's just a beep. I don't have to define that. I don't have to describe what a sine wave is. I just choose a note to play. And then the other thing is, like, what's the cool thing about numbers? What do numbers do? You all know? No, you don't know what numbers do. They go up and they can go down, right? That's what numbers do. So the thing is, right, and this is like, you're a programmer, right? So we use this notion of abstraction. And the cool thing about abstractions is you take an idea, like numbers, you can map it onto another idea which has similar properties, right? So what has similar properties to numbers? Pitch. Like the note of how high or low a sound sounds goes up and it goes down. And similarly, you can do the same with this. But the thing is, once you've got that, we can play notes which are higher, or really, really low like that, right? We can play these things. So we can play all the notes, and we can play notes in between, that's fine, like floats, whatever, right? So we can play in between notes. But at some point we need to play like sleep and one to make a melody. So I'm going to play that note, then this note, right? So now when I first implemented Sonic Pi, this is just pure Ruby. I've got a function called play. I'm using Ruby sleep, which is just going to ask the computer to sleep for a second at least, and then it's going to play note 70. And this worked perfectly well in the classrooms, but another thing is that in addition to trying to give children a creative experience with code, I also want to actually make a musical instrument. Right? I want it to actually be something I can perform with and play with, because it's really important to me to be able to go into a school and to be able to say, hey kids, you could do this if you practice and learn. Right? And it's not something which is impossible. All that stands in between you now and where you could be is just practice and play and experimentation. With the Ruby asleep, that doesn't really work. So, I mean, people keep talking about tests and types and stuff, right? I don't have any tests or types, right? Right? But, no, you shouldn't applaud, right? It's not good. I really love tests and I really love types, but it's not great for everything. But I mean, the software I write, I use in performances with 100, 300, 400 people. It's multi-threaded, right? And it works. And it's super reliable. So you don't necessarily need these things. But what you do need is proofs. So we have proofs about the timing model of Sonic Pi and how it works. This is a nice paper I wrote with Dominic Orchard and Alan Blackwell. And here we've got like a description of how Sonic Pi's timing model was initially implemented, right? And this is unfortunate. So the reason, if we're playing a few notes like play C, play E, play G, sleep for a second, play a bunch of the notes, sleep for half a second, what actually is happening is that the play function takes time to execute, of course, right? Because we're living in time and space, right? And so we have some delta A time that passes. Play E, we now know that delta A plus delta B, they're not the same. They're probably quite similar, but it depends on the scheduler, depends on the operating system, doing different things. And again, by the time we get to sleep 1, we've already incurred 3 levels of delta time. Plus, if the GC kicks in, again, more time, just randomly added. Then we sleep for at least 1 second. Not 1 second, at least 1 second. We say, I like to sleep for that 1 second, but after that, at some point, I'm happy to continue. Right? So in the Ruby scheduler, at some point, goes, right, you can continue, and then off we go again, right? And we can see we're just adding up all these delta times, so that actually the timing we're at this point now is not 1.5, it's all this stuff, right? And so if we have a live loop or a loop looping round, or actually what we're seeing is a drift in time, right? If we have 2 loops looping round, especially on a really slow computer like a Raspberry Pi, because this stuff runs on the Raspberry Pi, these deltas are actually quite large numbers. And you very, very quickly have this lack of synchronization because these numbers add up and they're different across threads. So this is a problem, right? So the solution I came up with was to re-implement Ruby sleep. So when I write sleep in Sonic Pi, this sleep, that's Sam sleep, not Ruby sleep, okay? But it looks the same, which is good. So I don't have to worry about explaining to kids. And the way it's implemented, going down here, no diagrams, is like this. So what I actually do is I have this notion of virtual time. And virtual time is just a thread local variable, okay? Starts at 0. And when I do stuff, it doesn't increase the virtual time, right? So the virtual time is still 0 after I've played the 3rd note. But of course, the real time is moved on because the actual computation takes real time. Now, when we do sleeping, we actually make sure that the real time is at 1, right? And then we increment the virtual time. So how do we do that? Super easy, right? When you start the program, you capture the time. When you sleep for 1, you sleep for the difference between what you want it to be and what it actually is, right? So sleeping is a delta sleep, not a real sleep. Okay, so I'm not worried about sleeping for at least. I'm not doing that at all. I'm sleeping to making sure the time synchronizes with that thing. And again, we do the same thing. So we're getting these deltas which are occurring only between the sleeps, but actually at the times, we actually make sure that we resynchronize the thread with the actual virtual time. And what's also really important, because of these delta times, this would make potentially this note just slightly after this note. And I really want them to be exactly the same time. Because these are not necessarily notes. These are effects which have very, very, very fine-grained time. I want them to be spot-on time with other effects. So this delta is not acceptable. And so what I actually do is I have a schedule ahead time. In this case, it's what am I adding? Half a second. On the Raspberry Pi, that's what's needed because the Ruby process is drifting around so much that have this half a second. On the Mac, it's much less. It's like 100 milliseconds. And then, because a play, the way it works is I actually send a message over a network to an external process, which is actually making the sounds. And so this virtual time is the time I'm actually sending. And actually the time I'm sending is that time plus the actual fixed starting point. So when I actually start the process, I capture the time, and every play is at that time plus this virtual time. So it all works very nicely. And what it also means is that the thread itself is in synchronization with the actual time we want it to be. So, and the cool thing is that if all this delta stuff is far too great, actually, so we're actually the real time is actually greater than where it should be, the sleep just falls through. It doesn't actually do anything at all. Don't sleep for any time. Okay, and then at some point, if we're too far behind, then we actually raise an exception. We say timeout exception. I can show you this. And then we have, like, if you're interested in these kind of things, Dominic has made some beautiful, like, Haskell proofs to prove this as sounds. So that's all there if you want to read that kind of stuff. So let me just quickly show you this. So if I ask it to sleep this, and actually do a kernel sleep for, I don't know, a second, and play note 80. Oh, that's actually working. That's a nice thing. Why is that working? Oh, don't worry. If I ask it to... so what kids would always do, so this is a thing I would observe, is they would create a loop like this, play note 80 and sleep and ends like this, right? So what am I asking the computer to do here? Right, this is what I ask the kids. But when they'd actually done this, their Raspberry Pi is locked, and we have to like a hard reset. But I say to the children, what does this even mean? This is asking the computer to play an infinite number of notes in 0 time, which is clearly not possible, right? So let's try that. Protect your ears. Right, and it dies, right? So we have timing exception, thread got too far behind time, right? So it tried to do it, and then like, luckily my system decided that was too far and then killed it off, right? So this is a really important thing to be able to work with. So the important thing is, like, the mechanism for time is really important to be able to deal with the fact that we want to be on time and we don't want to be too far behind time, and then we schedule everything to be exactly the right time, as close as possible. Does that make sense? Right, I don't know how long I've got left. Oh, I'm going very slowly. So that's play and sleep. The next thing was, right, so once it got that, we could start to teach, like, basic things like loops, and, like, I want to make a melody 3 times, do play note 80 or 70, sleep for a second, end, whatever, right? And combine that with play note 90. So the kids could go nuts and then do interesting things, and we could teach some fundamental computing science, teach loops, we can teach iteration, teach conditionals, can teach randomization. But what happened was the kids would, like, write a cool melody like that, and then would write, like, they'd want to do that with a bass line. So loop do sample bass drum house, my favorite one, and sleep for a second. Right, so they're like, I've got the melody, but I've got the bass drum, but I want them to play at the same time. How do I do this? Right, and this is not what I expected, right? So normally you teach concurrency university level. But these are primary school kids saying, how do I play the bass drum? They say, well, it's an obvious question in a musical context. So, like, okay, we need to teach threads. So I have yeah, seriously, right? And I do, and actually the kids learn it very easily. So I initially built this thing called in-thread, right? So this is not the same thing as a Ruby thread. It's built on top of a Ruby thread. And it allows me to, so basically it has the same kind of properties. I'm going to run this closure inside the in-thread on a separate thread, so that the play 90 is going to happen at the same time as the play 70, and then this bass drum house is going to happen at the same time as 90, because there's no sleeps in between. So you can hear 3 things at the same time. Then this is going to go round every half a second, and that's going to do 2 more 70s. Let's hear that. No, not any action whatsoever. What's going on with that? Have I killed it? Oh, I've killed it somehow. Wow. Let's reboot. What did I do then? I asked it to play an infinite number of things, and then... Right, okay, it's working now. So they played 3 times, then we had the bass drum going round. So being able to do this at the same time was really important, and so they were able to make their melodies at the same time. But then it became really useful to me to be able to think about extra things on top. So once we've got threads, and once we've got play and sleep, once we've got the basic constructs that Ruby gives us for like iteration and conditionals, we had a lot of cool tools to teach computer science. But then I was thinking about, how do we move on from that? How do we actually think about teaching music? How do we think about using this as a musical instrument? This, so far, is something which has got good sound timing, it's got concurrency, but it's lacking certain things. First of all, I'm only making a beep, not super musical. And then also, there's like lots of things I really wanted to do from overtone, like bring in effects. How do I add reverb to this? Right? Have anyone ever used any live coding systems that have effects in them? Like, just think about it from, one person. Think of it from a programming perspective. Normally what happens is, if I want to play this thing through an effect, I'd probably have to do something like create an effect. So like some sort of reverb.new or whatever, R equals, and then somehow have some operation that pipes it through R, and then usually what would happen is it would be in here or something like this, because you don't know where the kids are going to write this stuff, right? So they're going to create new reverb, they're going to play something through the reverb, through some weird syntax that I haven't created. This is not going to work, but just imagine it. But this time, what we're actually going to do is going to create three reverbs, right? And then those reverbs are going to continue running. So we're actually consuming resources at this point. So we have to tell our children it's not just enough to be able to know how to construct a new reverb and how to pipe the sound through the reverb. You've got to consider killing the reverb. That's actually the most hard, tricky thing. So at some point, you're going to think, well, where do we kill the reverb? Well, maybe we need to have some sort of way of creating a variable which represents a running synth, and then maybe like synth on destroy or something. I'm going to kill the reverb, do r.kill or something, right? We're starting to get really easy to teach this in the classroom with our 1 or 2 sentences. Then the problem is at this point is that maybe, well, this is a simple case, right? And that's not, this would work, right? You can imagine this working. But what if the in thread was here, right? And we have some stuff happening here that we don't know how long it's going to take. Maybe it's sleeping for a random amount of time, right? And then maybe we've got like T here, which is another play. Right, we're also feeding the reverb. So now we need to do maybe this T.on destroy. So we're starting to actually scale our complexity about how to reason about creating just a simple blooming effect. All I want to do is make a reverb, and for it to work. I want it to work through the threads. And also, I don't know, here I'm explicitly saying play, but maybe I have a function which 3 times do play 80 if rands is less than 1 or 0.5, right? And now I can't necessarily capture these as variables. It becomes much harder to track these synthesizers to make sure that it all works, right? And so the thing is that this is looking ridiculous now at this point to try and teach 10-year-old how to do this. Like we are working on like callback mechanisms or some sort of promise mechanism, which is waiting on the completion of synthesizers. We've got some way of, we want to be able to actually make sure that the thread is completed before we do all this stuff, because it might continue to create new synths, or we might spawn more threads which are creating new synths. So it's really important to be able to wait for all of the threads and wait for all the synthesizers to complete before killing the reverb. But even then, you can't kill the reverb, because if I make a sound which is going to last for a while, or even a very percussive sound, then I kill the reverb when the block's finished, then that reverb's going to cut out. What I really want to do is the reverb to decay through time nicely, or if it's an echo, to decay through time nicely. So I need to also wait a little bit of extra time for the effect to complete before I actually ask it to die, which is a lot of work, right? So what do? You actually think about a system which does all this, but wraps in a simple construct. So the real thing is, like, we don't need any of that, we don't need any of this, we don't need any of this nonsense, get rid of that, get rid of this, right, there we are, that's fine, whatever that was. This, we don't need that, or this, where are we now, are we getting there? Right, so, let's get rid of this for the moment, because we're not talking about concurrence anymore. So, I want to add reverb to all of this. How do I do that? Well, let's think about this. And this is the way you think about language design. What is the simplest thing you could write to say reverb? Well, you say, I'd like to start the reverb somewhere. Let's start it on the outer context. And where do I want the reverb to end? Here. Done. That's with reverb, right? Or if I wanted it with echo, here. Or with echo. So any code, whether it's got threads, whether it's got iterations, or whatever, sleep for a random amount of times, will actually work. So this reverb block does all that stuff I just described for you, right? So I don't have to teach the kids this stuff. And you can even see it working in the logs back here. Like this is all like the messages which are sent to SuperClient, the synthesizer. If I have the simplest thing I could write, like play 80, you can see actually that one play 80 has caused all these messages to go through, right? I'm creating synthesizers and groups and modifying them. But you can even see here that I'm actually asking the echo to be killed at some point. So it's automatically sort of tidying up the work after me. And it's doing all this stuff for me. Like even like you can see all this nonsense here. These are all the parameters you pass, or the options you pass to a synthesizer, which are defaults. So it does a ton of work, just even like with one effect and one play, that's sort of hidden behind the scenes. This log is great for debugging and understanding what's going on, which is what I use explicitly. So that makes sense. So now I've got this mechanism where what I'm doing is in this closure, I am capturing time. Right? I'm closing over time. I'm closing over threads. And so it doesn't just say, I want this to play 80. I'm also talking about, I want to make sure that I'm waiting for all the work inside there and define what that work is to be completed before I tidy up the echo. So this is really quite interesting. So I really wanted it to be as simple as possible so I could show it to a 10-year-old kid. And it turned out to be one of the most complicated things I've ever built. If you look at the implementation of this, it's just a horror show. It's serious, it's like a 100-line function, right? It's brilliant. And I try to tidy it up and I break it every time, but it really is super reliable. I fix points of reliability right now, but at some point I'm going to revisit it and rewrite all the underlying things, because when I designed this, I didn't really know what I was building. So you can't really write tests for that. I tried to do the TDD thing a long time ago, but it's just a horror show. Unless you like a fixed thing, you know what you want to build, then it's fine. But when you're really exploring and having interesting ideas, then that doesn't work very well. So it was important for me to think about what was the simplest thing I could build, and then try and make sure the system honored that. And so this is the simplest thing I could imagine writing, and I wanted to be able to make it possible for children to write anything inside that do-end block, and for it just work, and it just works. Right, what else should I talk about? I told you to talk about in-thread with effects, live loop. Now, this is the other thing. So once the kids had the in-thread, right, so now they can do this, and they can say with effects, reverb, do, loop, do, sample, bass drum, house. There's all stuff I've shown you already, which is great. Right, so that's going there, and then maybe have another one of these things, and then we want to do like, I don't know, ambi lunar lands. Sleep for 4 seconds. So I know we've got a reverbed bass drum and this lunar land going at the same time, and we're using all these constructs that we've just described. What's actually happening here, we're creating a new reverb every time we go around the loop. No, we're just creating it once, and it's capturing over the loop. So this reverb's going to be open until I kill the thread, then it will die. And similarly for this guy as well. And you can put them inside, that's no problem at all. So if I swap this round, this is going to work. In this top one, I'm creating a reverb every time round. In this one, I've only got one reverb for the loop. And so this is a bad form typically because I'm using a lot more resources. And these reverbs are overlapping, but it can create interesting effects. But the kids are doing this, and I went to a primary school. So these are in the UK. So these are like 10-year-old kids, like 9 and 10-year-old kids, and they had created their own Sonic Pi bands, and they had taught themselves this syntax themselves. Right, so I'm saying to you that maybe this looks complicated. I'm using threads, I'm using blocks, I'm using reverbs. But the kids, they were doing this. And they submitted a piece to the BBC for this thing called the 10 Pieces, which was creative responses to classical pieces. And they became a finalist. And this is how I knew about them. I watched their video, it was amazing. And so this is something that 10-year-old kids can teach themselves, right, with just reading a BIM tutorial. But the thing was, I also wanted to be able to do live coding. I wanted to be able to modify this on the fly. So this is enough for composition, right? So I can talk about things happening at the same time, But what I've got here is something which I can essentially press play and listen to. But I can't change it, I can't modify it, I can't go on stage and perform with this. I could just start one piece up, press stop when I've had enough, maybe go to another buffer, start another piece up and do it like that. But I really am interested in changing things. And so there was a really easy way to figure that out. So if I create a function, define foo, which is going to have this body here, I can do this. And now I want to change the bass drum house to choir. It's working nicely. But what I've actually got now, if you can hear that, I've actually got two choirs being played. If I try and change it to something else, maybe like a play 80 release 0.1. There's actually 3 releases now, because every time I press run, it creates this function. That's fine, we understand that. It creates a new thread, right, which is looping, calling that function. So I press run 3 times. I have now 3 threads, all calling foo, with slightly different phase offsets. And then I've also got 3 loads of these ambilunar lands. So when I'm live coding, I don't want to necessarily be adding new things. I want to be changing the things which already exist. So how do I do that? Something, you know, that's a tough thing. So then I created, and the reason why I've got this in thread is because, many reasons really. The way it works is that it's all about thread local. So these threads have their own logical clock. So that timing thing I showed you before, this stuff, where are we? This stuff here. This logical clock here, this virtual time, there's one of those per thread, right? So each thread can have its own time. There's no global BPM. There's no simplistic thing like that. I can do quite interesting phase patterns with this by having the different threads operate with different speeds. That's all totally possible. And so the in thread allows me to store the current time and the current synthesizer. I can change the synthesizer at the top here. Use synth TB303, play notes 60, cut off 70. Like this works, right? Because this use synth at the top defines a thread local variable saying this is the current synthesizer. This function has no idea about that. It's not closing over that at all. But this thread inherits the thread local variable, so its local synthesizer is a TB303. And so when it's looping, calling that function, that's then set as a thread local, so that function's definition, it is able to know which synthesizer it is because it asks the thread, what is your current synthesizer? So this inheritance thing works really well. And so I have the in-thread for that, but I also have the in-thread because I can give them names. So if I look at the documentation, I can say, look, I can give a thread a name, make this thread a name thread with name. That's a really good documentation string, I should fix that. Name, foo, like this, and I give this one a name, name, bar, like that. Oh, undefined method name, because I need to give it a keyword. Super annoying Ruby syntax, right? So this works really well. So now I've got the same thing as before. They've got names. They're actually then, that name on the logs, if I make the logs bigger, you can see that it's telling me the names of the threads here, which is super useful, so I can actually debug and figure out what's going on. So the names work really well. But the real reason for having names isn't just for the logs. It means I can change this thing here, and I'm not adding new sounds, right? So what the name threads do is they basically say, if there's a thread with a name, I'll create it, that's great. And if I try and create another thread with the same name, it's a null op. Right? It doesn't allow me to do that. So only one thread with a given name can exist at one time. So that allows me to do live coding. So this is what, this time last year, probably when I gave a demonstration at the keynote last year, this is the state I was at, right? I had the ability to do this kind of live coding, which was basically creating functions which were dereferenced by threads, which were names, which then allowed me to basically just do what I just did then, live code by just redefining functions, and not necessarily creating new threads, but using the threads which currently exist. But this is getting to the level of complexity of the with effects thing, where it's starting to get hard to teach kids how to do this, right? You've got to create functions, you've got to give threads their names, you've got to loop in the function, loop in the thread, calling the function, right? So this is tricky. So this is where you like think about how do I, as a programmer, what's the solution to this? Is to create a new abstraction, is to create a new way of thinking. And so there's a thing now called the live loop, which is called foo, which I can do exactly this. So I can take the body of this and put it in here. And this live loop here is a contraction of all of this nonsense down here, right? So the live loop is three things. It's a function called foo, right? So this will define a function called foo with that as the body. That's the first thing it does, right? And so I can, let's just look at this. Let's get rid of all this stuff. If I create this, well, we have the same behavior, but in another buffer I can call foo, and I can get the value of it, right? So that's working. Notice that over here, it's playing it with a beep, because the current synthesizer is the beep. Whereas here, the current synthesizer is TB303. So the thread local thing really does work. All I'm doing here is calling foo, which is calling the body of that live loop just once, because it's just a function. Okay? And then in addition to that, it creates a named thread with the name foo. And so that then has the body, which is to loop calling the function foo. So now we've got two things called foo, a thread and a function. And the thread is calling foo, the function, repeatedly. And then that allows me then, so if I run this code, if I start it off and change the code, what actually is happening there is that I am redefining the function, which is why you're hearing the behavior change, but I am not redefining the thread, because the thread is already named and one exists. So I have this ability to change it on the fly. And now we're in a position where I can teach this to 10-year-olds again, which is brilliant. Right, so I'm seeing 10-year-olds using this stuff, and it's really trivial for them to pick up. And they can actually start to live code now, because this construct is much easier to work with. Now, the one last thing I wanted to talk about is the Q-sync mechanism. So what's interesting now is like the last two abstractions I've just described are not that useful for teaching the curriculum for computer science. Right? Concurrency is not really in the curriculum. That was like an extension. That was where I started to break out of that. But live loop, that's not in the computer science curriculum. Who knows about live coding in school? That's nuts. And with effects, what the hell has that got to do with teaching sorting algorithms? Right? So these are not ideas for the curriculum, but what they are ideas for is for engaging people in the curriculum. And there are ideas for having a lot of fun, because that's why you engage, is because it's a load of fun. So with effect, allowing me to really have fun changing the sounds, changing the properties of the sounds. The live loop allows me to do performances. So if you saw me perform last night, all I was doing was creating these live loops. I had a bunch of them going and changed them on the fly. That's all I do. So you can totally do this as well. It's super easy. But one thing that happens when you're performing is that I might have a bunch of these things. So let's have live loop foo and live loop bar. And in this one, all I'm doing is doing the bass drum. Right, so now we've got this concurrency, which is great. So if I want to make the bass drum go faster, that just changes to smaller time. Right, or slower. But now I'm going to introduce an error. Got an exception. So there's no thing called desample. Did you mean sample? Yes, I did mean sample. Okay, thank you. So I then fix this up. Oh no, so it's working, but they're out of sync. Well, they're actually out of phase, so they're in synchronization. This is sleeping every second. This is sleeping every half a second, but they're out of phase. So if you're like doing a bit of dance on the dance floor, this is not necessarily what you want. You want everything to be like on time. So how do you fix this, right? The simplest way to fix it is to stop everything, because as we know, when we start the program, we have a virtual time of 0. And those virtual times are inherited by both of these live loops. So when I start it again, they both start with the same time, and it's on time, right? So that's one way of working. But can you imagine, right, when you make a mistake, you've got to kill the whole sound, right? People dancing on the dance floor, like, what's going on? Oh, okay, he's made a mistake, and then fix it, and now we can start dancing, right? So the solution to this is like you need a way to actually to be able to fix it without stopping the threads, right? So this is another problem. How do I do that? So any ideas how you might do that? You should know, because I've already told you the answer. It's called Q and sync. Where's the cheat sheet? There is the cheat sheet. Cue and sync, right? So what is cue and what is sync? Well, we actually noticed, well, what I have as a way of saying synchronise on foo, play, sample, ambi, lunar lands, right? Play. Oh, there's no sound. But you can see on the logs here, I'm synchronizing on foo. So that thread is blocked. Still running, it's still alive. If I had effects, if I stop this and I put an effect around that, right, that effect has been created. There's a reverb running in Super Collider right now on that machine. It's really exciting. You can't see it or hear it, but you've got to believe me. But actually, you don't need to believe me because if you look at the logs, you can probably see that if you can find the right bit, there's definitely a reverb in there. So the thing is that what I've got is a mechanism for blocking. So kind of like a closure promise. So and it's how I've actually implemented these things. And so it's just blocking on the thread. So what I need to be able to do is from another thread, cue foo. And when I run this, it's going to send a heartbeat message to the whole of Sonic Pi's runtime system, and any threads which are blocked syncing on foo will then wake up and make a sound. Let's see this happens. Let's run this. Hey, look at that. And you can actually see here, over on the logs here, to make it clear, that each thread has, well, each run, which is when I press the run button, is like the main thread, has its own unique ID. It's an incrementing integer. So 35, which is I ran before 36, was syncing, and then you can see that it's actually synced, and it's also inherited the BPM. This is the clever bit, and then played a sample, played a note, and then it's finished. And you can also see here that 36 has cued it out. So this is what you can see here, like there's a race condition in terms of which gets printed first, but it doesn't really matter in that sense. But what really is important is that we have now a way of asking something to wait for something else. And what's really useful is that, if you notice over here, if I move this over here, like, no, not this, this, if I get rid of, comment this out, we should notice that every time this loop goes round, we're actually calling a cue message. So by default, live loops send a heartbeat every time they go round, right? No one's listening to that, no one cares about it, but it's there, right? And so this is the fourth thing that live loops do, is they auto cue every time they go round. You can disable that if you want to, but they auto cue. And the really important thing, like I've got 1 minute left, is that it's not just enough to wait for something to say go and then go, because we enter the same kind of problems we have with this, because we're going to have some delta t between someone saying go and then you going, okay, I'm going, right? Because the scheduler has to tell you to go. So it gives you some CPU time. And so what I've just described is not enough to be able to fix that. So the final piece of the cake, the final thing, is that when I sync and cue, the thread which creates the cue message also sends out its current logical time as part of that message. So the thread which then gets synchronized with it gets its own logical time completely clobbered and is replaced with the local time of the thread which created it. So that way, we have absolute guarantee that these are completely in sync with the same time, and also it inherits the BPM, which is the thread local. So just as a final demo of how it works, it's going to be amazingly glorious. If I start these off, but then I make a mistake, boom, oh no, fix it up. Now you can hear they're out of sync, right? So all I need to do is ask it to sync with foo. Now it's back in synchronization again, right? So it totally works. So if you're performing and playing, you're totally able to make mistakes, have only part of the system go down because only the thread which made the mistake dies. The rest of the music continues, as you heard. Then you have an ability to fix it and sort it out whilst the music's still going, whilst the people are still dancing, thinking, well, there's a bit of sound gone, but it's still pretty good. And then you kick the kick drum in, and then they go nuts. And it's also a way of like adding drops, and adding beats. And when you wanted to, you can sort of set a bunch of live loops up, ready to go, syncing on something, and then you can cue it in one go, and you can sort of create multiple live loops at the same time and trigger them. So you can sort of set things up, stage them up, and fire them off at the same time. If that makes any sense. So hopefully that makes sense. I've just tried to give you like a background of some of the interesting sort of ideas I've had to implement, the motivations why, to make these things possible, to make it easy to teach to a 10-year-old, and also a tool that I can use to perform with, and more importantly, a tool you can use to perform with. And I really hope you do. I really hope that you can see that actually this is not too hard to get started, right? And just to finish, I've already 1 minute over time, but there's a help system with a complete tutorial for you to read. It's written for you. It's super simple. And then there's a bunch of examples. And all you need to do is copy and paste an example. And because we have music as text, it really just does allow me to create music by writing text, right? And this is a beautiful thing. And this is just liveness. 1, 2, 3, 4 liveness. And there's nothing more complicated than I'm explaining to you. And I can just change these things. Right? And I can modify it. Create rings. These aren't all like these. This is cool. There's lots more cool stuff in here as well. A comment actually is really cool for actually not to play something. So what I think is a comment is a way of communicating to other programmers or yourself, but I use it as a way of mixing in and out sounds. So I've actually commented these out. It's live and it's still running, but I've only got only one making a sound. So hopefully you can see that this is all a thing that you can use right now, and hopefully you can also start to see this is something you can show and share with other people. Because one of the things that frustrated the hell out of me is that I have such an exciting interest with programming, but only people like you would listen to me, right? Which is brilliant. Thank you so much. It's fabulous. But yeah. But there's a lot more people in the world that could also enjoy this. And so hopefully tools like this will help us help other people understand these things with greater clarity. So please spread the word. Please give me some feedback. Please play with it and share your joy of coding with as many people as you possibly can. Thank you very much.